Differential equations. Like the last video, this one considers another prerequisite, this time integrals. This video, like the one before, is not a complete course, in this case on integrals, but rather a recap of the most fundamental concepts in this topic. So, let's just dive in. When we discuss integrals, we typically think of two types of integrals, indefinite and definite. Indefinite integral can be thought of as the antiderivative of a function. When we integrate a function, we are essentially trying to find another function whose derivative we are integrating. That might sound kind of circular, so the algebraic expression might clear some things up. We might imagine that we are integrating a derivative of some function. This will give us the original function f of x plus some constant c. The reason we have this constant is because when we add a constant to a function and we differentiate that whole expression, we are still going to get the same derivative. For example, the derivative of x squared is 2x, but the derivative of x squared plus 5 is also 2x. That means that when we try to integrate these functions, we are always going to have this constant plus c in them. We can also demonstrate this in a more rigorous way by considering how unique the antiderivatives really are. So suppose we have some function g of x and then some other function h of x, and we take their derivatives. So we have g prime of x, which is the derivative of g, and h prime of x, which is the derivative of h of x. If those derivatives are equal, then what we might do is we might take the difference of those two functions, we might try to differentiate that difference, and by the property of linearity of derivatives, we get that this derivative of a difference is a difference of derivatives. That is, we have g prime of x minus h prime of x. Now, given our initial assumption that those two derivatives are equal, this difference is going to be equal to 0. Now, if we consider the leftmost part of this equation, that the derivative of g of x minus h of x is equal to the rightmost side of the equation, which is 0, we can consider what the implications of this are. If you've encountered mean value theorem before, you might know that it implies that if some function f of x, if its derivative is 0, then that means that the function itself is a constant. For example, a constant c. In our case, what we've set to 0 is the derivative of the difference of the functions g and h, meaning that g minus h is a constant, or we could say that g is equal to h plus some constant. This means that antiderivatives are unique up to a constant, which is what we've essentially been shown in the last slide. Another type of integral is definite integral. It represents the area bounded by the graph of a function. Specifically, if we have this notation of integration between points a and b of our function f of x with respect to x, then that definite integral represents the signed bounded area between x is equal to a and x is equal to b. We can visualize this using this diagram right here, where we have some function f of x, and the areas above the x-axis are viewed as positive, and the areas below the x-axis are viewed as negative. We can compute the definite integral by considering the difference of the antiderivative evaluated at points a and b. Specifically, if we have a definite integral of our function f of x between a and b, then that definite integral is equal to the antiderivative of our function evaluated at b minus the antiderivative evaluated at a. We can show this by defining some function g of x, which has a similar form where we have an integral from a, but in this case the upper limit is x instead of b. And to avoid duplicate variable names, we have f of t with respect to t inside the integral. We might take the difference of f and g and differentiate that. By the property of linearity of differentiation, we have that this is equal to f prime of x minus g prime of x. Now, because the derivative of both of these functions is lowercase f, that difference is equal to 0. So similar to what we've done before, we can say that these two functions, uppercase g and uppercase f, differ only by a constant. That is, we might say uppercase g is equal to uppercase f plus c. Then we might plug in x is equal to a. Then we have f of a plus c is equal to g of a, and then we can look at the definition of g to see that this becomes the integral from a to a of our function f of d. Now, if we integrate from a to a, that is going to represent 0 area, meaning that the value of this definite integral is 0. When we then look at the leftmost part of this equation and the rightmost part of this equation, it becomes evident that our constant c is simply minus f evaluated at a. So far, we have the definite integral from a to x of f of t with respect to t equal to g of x, which is uppercase f of x minus uppercase f of a. So we have this expression, and the final thing we have to do is set x is equal to b to get the integral from a to b of f of t with respect to t equal to uppercase f evaluated at b minus uppercase f evaluated at a. By considering many of the derivatives of common functions, we can use a reverse process to find what the integrals of various functions are. For example, if we have x raised to some power, a, then the integral of that function is going to be x to the power of a plus 1 divided by a plus 1. For the special case when a is equal to minus 1, that is when we have 1 over x, when we integrate that thing, that is equal to natural logarithm of the modulus of x. The integral of sine of x is minus cosine of x. The integral of cosine of x is sine of x. And the integral of e to the x is e to the x itself. And note that all of these indefinite integrals, of course, have a plus c in them. Just like with derivatives, it's interesting to understand what happens when we have more complicated functions. For example, what happens when we have sums of functions? Suppose we have some function, f of x, which is defined to be f1 of x plus f2 of x, where uppercase f1 is the antiderivative of lowercase f1 and uppercase f2 is the antiderivative of lowercase f2. If we now consider the sum of those two antiderivatives, that is uppercase f1 plus uppercase f2, and we take the derivative of this sum by the linearity of differentiation, that is going to be equal to uppercase f1 prime plus uppercase f2 prime, which individually we've just defined to be lowercase f1 plus lowercase f2. Now if we look at the leftmost part of this equation and the rightmost part of this equation, it becomes evident that uppercase f1 plus uppercase f2 is the antiderivative of lowercase f1 plus lowercase f2. This means that when we integrate lowercase f1 plus lowercase f2, we can express it as uppercase f1 plus uppercase f2 plus some constant. But we know that individually, uppercase f1 is the integral of lowercase f1 and uppercase f2 is the integral of lowercase f2. To spell it out, this means that the integral of a sum of functions is the sum of the integrals of those functions. In a similar fashion, we can consider what happens when we scale functions by certain factors. For example, what happens when we define some function f of x to be equal to k times f1 of x, where uppercase f1 is the antiderivative of lowercase f1. If we now consider k times uppercase f1, and we take the derivative of this thing by the linearity of differentiation, we know that this is going to be equal to k times uppercase f1 prime. And we know that uppercase f1 prime is just equal to lowercase f1. If we consider the leftmost part of this equation and the rightmost part of this equation, it becomes evident that k uppercase f1 is the antiderivative of k lowercase f1. This means that when we integrate k times lowercase f1, that is just going to be equal to k times uppercase f1 plus some constant c. And we know that uppercase f1 is just the integral of lowercase f1, meaning that we can rewrite this as k times the integral of lowercase f1. This means that the integral of a scaled function is the scaled integral of that function with the constant of scaling remaining the same. This is illustrated in this equation right here. When we combine these two results, that is the integration of sums of functions and scaled functions, we find that the linear combination of two functions integrated is just a linear combination of the integrals of those two functions. We can extend this to a linear combination of any number of functions, just like with the derivatives. This means that integration is a linear operator. The reason this is important is because it means that complicated integrals can be decomposed into simpler integrals for which we know the expressions. For example, if we integrate 2 times e to the x minus x to the 4 plus 5 cosine of x, we can express this as 2 times the integral of e to the x minus the integral of x to the 4 plus 5 times the integral of cosine of x. Because we know the expressions for the integrals of e to the x, x to the 4, and cosine of x, we can substitute in those expressions, and we get that this whole thing is equal to 2 times e to the x minus x to the 5 divided by 5 plus 5 sine of x, and we have a constant plus c. To summarize, indefinite integrals are antiderivatives. Definite integrals represent areas bounded by the graph of the function and the x-axis between points A and B. We also found that many of the antiderivatives can be found by considering the derivative functions, and we have shown that integration is a linear operator.